My name is Justin Pearson. I'm a fourth year graduate student in ECE, and I've found a lot of success using Mathematica for various things in school and when I was working at an aerospace company, and now in graduate school. And I thought I wanted to sort of evangelize it and share it with you. So I guess a good point to start is, like, what is Mathematica? And if you ask the random person on the street, I don't know if you guys read The Onion, but they do these, like, random people on the street. You'll probably hear things like, well, it does symbolic manipulation, or it's like Matlab, but you do math with it instead. Like, not like real math, not like engineer math, like Matlab math, but real math, okay? Or, it's the thing above Matlab on the start menu or something. This thing that I clicked one time and it was totally confusing, so I shut it down. Okay, and so I guess I want to just give you a real quick elevator pitch of what Mathematica is, or what these people think Mathematica is, so that then we'll all be sort of on the same, we'll be able to be on the same level. We'll be there with the average man and woman on the street. So you open up Mathematica, you're looking at sort of a blank page. They call this a notebook. It's sort of like an M file in Matlab. And if you type, can you see this in the back, folks? Okay. And if you type solve of ax squared plus bx plus c equals 0 for the variable x, you'll get some sort of result that has some curly braces and stuff, but it's essentially saying that x is, the solution for x is the solution with the quadratic equation. So there might be some weird things here. You might see, I actually cannot point that high, so I'm going to use this super pointer. You might see that, whoa, there's like a superscript there, and this is a hint that this is not your standard text editor. This is not like writing a Matlab M file. You have access to more characters than just what's there on your keyboard, and in fact, the ability to do sort of nice typesetting, like have this superscript 2, is just one of the nice typesetting features that you can do in the so-called Mathematica front end. Okay, so that's great. So it does symbolic manipulation. It's solved for x. That's great. So here's another thing. Suppose you have a differential equation. So you have x double dot plus 3x plus prime plus 2x equals 0. You have some, I guess I will have to use this pointer. I'd rather just sort of jump around, though. You have some initial conditions. You want to solve for x of t. T is your independent variable. The d in the d solve here means differential equation solve. Okay, if you do this, bam. Right out of the gate, it'll show you x of t goes to this function of time. So this function of time, if you plug it into the differential equation, you take the derivatives and so on, will satisfy x double prime plus 3x prime plus 2x equals 0 for all t. Okay, so that's nice. So it can solve some math problems. Okay, so far so good. Because this is not your standard issue text editor, you can do very elaborate mathematical typesetting. And one of the things that Mathematica can do is there's a little palette that comes up. You can push, okay, I want to do like an integral. I want these to be the bounds of the integral and so on. But there's also keyboard shortcuts, which makes it very easy to put in this. This looks a lot like the math that you would write down in your math classes. So here we have a couple of different integrals. The integral from minus infinity to infinity of sine x over x, and then of sine ax over x. And if you do both of these things, it will say, the answer to the first one is pi. If you do this infinite integral, it turns out that the integral under the sinc function, it's an electrical engineering thing, is pi. And if you have a sine of ax, where a could be some number, well, you get this weird thing here. So what this is saying is, this is it's said, I don't know what a is. It looks like it's some number, because it's like in this integral, it's multiplying x and so on. If it's a real number, so it's found a conditional expression. The value of that integral, conditioned on a being an element of the reals. So if a is a real number, then the answer is pi times the sine of a. Okay, so that's kind of cool. And if this is a complex number, Mathematica has not found some way how to simplify it. The integral does not converge. If this is like sine of I times x, the integral doesn't converge. Okay, so when the first time you see this, if you don't have a buddy sitting next to you, if you're computing without a buddy, this is just some weird symbolic output. It comes up with some weird output. There are ways that you can have Mathematica simplify this, but right out the gate, if you see this for your first time, this is like, this is too weird, close the program, let's just use Matlab. Okay, so this is something else that you might have seen before. And at this point, if you were to grab all your pizza and swag and run out the door, you would know as much as the average man or woman on the street about Mathematica. And you could probably do pretty well. You could solve some differential equations, solve some algebraic equations, do some integrals, help check your answers in math and so on.
So sine of a means sine a?
No, this is the function sine, and this a is just some.
Pi sine a. on output?
This here? Yes, SIGN is the function sign. So this returns +1 if it's greater than 0, and -1 if it's less than 0.
Oh.
It's just the sign of the number. Yep, exactly right. Okay, so at this point you know pretty much everything that the average man or woman on the street knows. Let me just show you one more thing, and then that'll bump you up past the average man or woman on the street, and at a cocktail party or something you can say, well, did you know that in addition to these things, Mathematica can also do this, do this. Okay. This is a long line, but let's just work through it. So the essence of this is we are going to plot the function sine of omega t plus phi. So this omega and phi are not characters on your standard keyboard, but there are little keyboard shortcuts to put in all the Greek letters so that you have access to things that make it look like you would normally have in a math class. So we're going to plot sine of omega t plus phi, where t goes from -4 to 4. Okay, that's what we want to do. But wait, omega and phi are not defined. We haven't defined them like we would have to say omega equals 1, phi equals 2 or something. But wait a sec, what if I just want to explore this function and I don't want to have to tie down variables of omega and phi? In the old days, I would have to say, okay, let's try it for omega equals 1, run it, see what happens. Let's try it for omega equals 2, run it, see what happens. What if I wish I could just have like a slider for all the omegas, and I could just, this slider would go and I could see the different omegas. I have a slider for phi, slide that slider, see what this plot looks like. And that's exactly what this manipulate function does. So you give manipulate some expression that you want to look at, and then some range of these other variables that it will produce sliders for. Okay, bam. And what you get is, you get some plot. Here omega and phi are just like 0, so the plot is just 0. But if you then mouse over and drag these things, you will see that you can plot sine of omega t plus phi. As you wiggle the sliders around, the plot will change in real time. So I think that's really cool. You have the ability to, in real time, just sort of as fast as you can think it, make a little GUI that lets you explore some mathematical behavior about something. And this is not just for plots, but any Mathematica expression that you put in here. So suppose you want to like factor some number, you can put like, factor integer of x, and then have x go from 1 to 10 or something, and just drag that slider around. You'll see the different factors of x. Okay, so now you know more than the average man or woman on the street. It has this very intuitive, interactive interface. Great. Okay, so now, you people in the front are like, this is kind of big. But we are squarely in the middle of Dead Week right now. And how many of you are Engineering 3 students? Just out of curiosity. Great. The reason that so many of you are Engineering 3 students is because Engineering 3 is the only class where I went in there and I said, hey, everybody come to my talk, because I really think that you guys are in a great position to expand your engineering tool set. And so anyway, I'm really pleased to see that so many of you show up. But if I were you, I would be thinking, learning programming is really hard. It's sort of in this intersection between panicked frustration, like the homework assignment is due in 10 minutes, it's like 11:50 p.m., and my code doesn't work, despite being the same as my friend's code, and unbridled rage. Why doesn't the computer do what I want it to do? I clearly am doing it right, and the computer's not doing it. So in the intersection of these two things is your programming language of choice, and here I am standing up in front of you saying, hey, why don't, in addition, here we are in Dead Week, what a great time to learn a whole new language. So, so the question that should be going through all your heads is, why should I learn Mathematica when I already have to learn Matlab? Okay, and I'm not saying that you right this moment have to learn Matlab, drop all your studying. Sorry, Professor Jeff Molis, I couldn't pass my test because Justin told me to learn Mathematica. But this is a question that is very natural. We are all creatures trying to minimize effort. We are all trying to minimize our expenditure of energy in the world. And unless I can convince you in the next half hour that learning Mathematica will make your lives better, it would be totally reasonable for you to just forget everything, eat your pizza, gather up your swag, and run out the door. So I've tried to partition this talk in sort of 3 ways. So here's the answer for why you should learn Mathematica. I figured it would be pretty accessible to a broad audience. Money, knowledge, and power. Who wouldn't want that, right? Okay, so let me explain why we should learn Mathematica in sort of these 3 terms. The first one. If you Google UCSB Mathematica, you will probably end up at this page for the Office of Software Licensing. And because the people who make Mathematica so desperately want people to use their software because MATLAB is so pervasive in the school system, they have struck a very generous deal with UCSB and many other campuses. That deal is summarized with this sentence: students may now access Mathematica at UCSB on their personal computers. Now so that means you can install this on however many computers you have. Your personal computers do not have to be bought by your professor or stay in your lab or whatever. Your personal computers, you can install it. Contrast that with the Matlab license, which is users should contract MathWorks directly for purchasing individual licenses. And indeed, the reason that Engineering 3 does not have a textbook associated with it that you had to buy, as far as I know, Jeff uses these PDF lectures, is because we already know that we're going to make you buy the throw down $100 for Matlab, plus any toolboxes that you want to buy down the road. So the Mathematica license is more generous than the Matlab one, because the Matlab guys know they already have you locked in. So, okay. In addition, you may not have run into this quite yet, but you probably will in the near future. The MathWorks, the guys who make Matlab, their business model is there are all these extra domain-specific toolboxes that you can buy extra. Okay, and that's kind of a drag. Like your friend sends you some code, you can't run it because you don't have the neural network toolbox or something. Or you're trying to figure out how to do this function. You go to the MathWorks documentation. Oh, it turns out you need the neural network toolbox. So this sort of limits your ability to freely code. Okay, in contrast, Mathematica, now they're trying to call it the Wolfram language because it sounds too mathy to call it Mathematica, but I'm going to call it Mathematica. Mathematica was designed to try to answer anybody's sort of computational question, to address any sort of computation that you might want to do. And so as a result, somebody, okay, I'll just cut to the chase. Somebody compared these two. They said, how many toolboxes would I have to buy in order to have the same functionality that I already have in Mathematica? And here's the answer. There's a big long list. I'm not going to read them, obviously, but things like the control system. So I'm a controls guy. I need to do control stuff. Turns out Mathematica, out of the box, can already do a bunch of control system stuff. That's nice. And it goes down the list. So all these toolboxes, their functionality is already built into Mathematica. That's very nice. Okay. Okay, so enough with the, yes, one more thing about the money front. They want it, they know learning Mathematica is hard. It has sort of a steep learning curve, but they've made great strides and bounds to make it easier, to lower the learning curve. And in particular, they've got a version of Mathematica online. So if you go to this Wolfram Programming Lab, you can see a nice little 5-minute video intro, and then try it out. So as soon as you try it out, you'll be looking at this web page where if you click in here, this is the part that kind of looks like a Mathematica notebook. And you can see, you can execute instructions, try new instructions. They sort of prompt you. I think you get to see the answer at some point, or they already have the answer here. You can evaluate it and change it if you want. And then you can sort of branch off from there. You can draw graphics and so on. Okay, so in conclusion, for the money part, Mathematica is free. We have a very good deal here at UCSB. We can install it on our personal machines for free. You don't have to buy any toolboxes. It can already do a bunch of stuff. And you can try it online. If you don't even want to go that far of installing it on your machine, you can try it online. Okay. The brunt of the talk, because we're all here in college, we're all trying to get a good education and so on, the brunt of the talk is here. I want to go through a couple of examples that I saw in your Engineering 3 homework and talk about how your lives might be improved if you attack it with Mathematica. Obviously, in Engineering 3, you have to learn Matlab. The whole class is, can you write Matlab? So it's not like you can say, hey, great news, Jeff, I did all my homework in Mathematica. In this Matlab class, can I use Mathematica? That's not going to fly. But in subsequent courses, it will be less critical what programming language you use. So anyway, I just want to talk about a couple of problems and show what it looks like in Mathematica. Okay, so the first one. So you probably remember this. This is from a few homeworks ago. But the idea is, here's an electrical circuit. Here are some equations that relate the voltage, the resistances, and the currents in the circuit. Please find the currents as a function of the voltage and the resistances. Okay? And packages this all up into some function. Great. So let's just see how this would look. And this is the part that's a little dicier because I'm going to be at my computer here. Let's see how this would look if we approach this in Mathematica. Okay, so what if I do this? Does that look okay? Okay, so the first thing to note here is that this is the Mathematica file. This is the electrocurrents3.nb. And it looks pretty weird. This doesn't look like your standard issue text file. And the reason is that because this is not your normal text editor, if I do something like I go to Format, Style, Title, now you can see these different cells over here. And I can say things like, my title, lol. OK, then below that, I can put in another thing. Maybe, I don't know, maybe a section. Here's my section. OK, so in this way, you can put in a whole lot of formatting stuff that makes it so that, years down the road, if you want to know how to do something that you've learned in college, if you have a single document that explains it, that has the problem statement there, has the solution, has the inputs and outputs and right next to each other so you can read it, it's much easier to read than if you just have, like my situation now is, for my college career, I have a whole pile of .m files, and I have no idea what they correspond to, and when they run, they produce numbers, and I don't know what those numbers mean. But having a whole self-contained document makes it so your college education can sort of help you long after you've graduated. Okay, so that's the pitch for why formatting is nice. This thing down here, this is not actually something that I typed out. I just took a screenshot. Well, let's see, do I have the thing? Yeah, I just took a screenshot, like on a Mac. You can just sort of take a little screenshot of something, and then went back into Mathematica and pasted it. So now I can get the problem statement, right readily at hand. It's just an image. I mean, this is not the most graceful thing in the world, but it keeps it self-contained. Okay, so you probably remember the Matlab answer for this problem, which is you make some function that takes these input arguments. You, by hand, have to figure out what the coefficients are in this A matrix, and then make a B matrix, and then use A\B. So this is how you take your problem, convert it into a linear algebra problem, and then solve the linear algebra problem using built-in stuff in Matlab. Okay, so that's how it works in Matlab. Let's see how you might approach it in Mathematica. Okay, so I pasted in the equations so that I could not lose track of them when I write them here. Here's some Mathematica code. I'm saying equations equals a list, so equations is some variable, but this thing looks really weird. I2 plus I3 equals I1. These are all like equalities. And because in MATLAB would complain and say, oh, these aren't variables. You don't have these defined in the MATLAB workspace. In Mathematica says, I do not yet know the values of these variables, so I will leave them symbolic. Once I know their values, I will be able to assess whether it is true that I1 plus R1 plus blah, blah, blah. Whether this is true, I can, if I know the values, I can boil it down into true or false. But since I don't, I'll just leave them symbolic. And that's what it does here. So this is what this variable equations is. It's a list of 4 equations. Okay, now, it's very nice. Turns out it's like the App Store. There's an app for that. There's an app for that. There's a Mathematica function for taking a list of equations and a list of variables that you're interested in and pulling out the coefficients. Here are the coefficients that multiply those variables, and here are the constant ones. There's a slight technicality with the sign flip that I don't want to get into, but here you're saying matrix form of A, matrix form of B. So coefficient arrays returns the vector and the matrix, and you say, please show A and B to me in the form of a matrix, instead of just a list like this. So you get this very nice output here, and if you'll notice, this A and B are the same as the ones that you would have had to compute by hand in the MATLAB code. This A and this B are the same. Great. So that's cool. That's, it just pulled those out for us. If you were doing this by hand, you could then check your answer or whatever. Let's move on. If you want to, so as you know, you're going to have to find x such that ax equals b. Fine. And so that means you're going to have to do something that looks like a backslash b, or take the inverse of a and multiply it by this vector b. Hey, Mathematica has no problem taking inverses of symbolic matrices. So here's the inverse of A. It's a 4x4 matrix. The elements are symbolic. This is not a problem. It can do that. If you then multiply it by B, so dot is how you do matrix multiplication in Mathematica, and algebraic and simplify these terms, make it a little bit prettier, it will give you these 4 terms. So these are the 4 currents, I1, I2, I3, and I4, in terms of the resistances and the voltages. You get the same answer if you use a built-in function, linear solve, which is essentially the same as a backslash b. It's more efficient than having to compute the symbolic inverse, but you get the same answer. So that's all very nice. You can see that there. You can see it symbolically, and I won't do this right here, but you can go through various thought exercises that will help you understand the problem better. Like, if R2 is 0, what happens? That corresponds to a short circuit somewhere. Does it make sense? Does the corresponding current like go to infinity or whatever? Or what? So when you have this form here, you can learn a lot more about the problem. Okay, so let's see. Okay, once you have the currents, you could actually plug in values for them. So this percent is sort of like MATLAB's like ANS. It's sort of like the previous answer. Take the previous answer, and // is a Mathematica command saying, I'm going to give you a bunch of rules to substitute in. So please substitute in v equals 5. Instead of having v, put in 5. Instead of R1, put in 100, and so on. So you're putting in actual values here. And what do you know? Here are the 4 currents when you actually applied these numbers into it. So this is sort of a substitution rule that you've defined. This looks weird if you've never seen it before. This is like, well, it's sort of like I'm calling a function, except it has this really weird format, and there's this dot slash and everything. Don't worry. You can still define a function the same way that you could in Matlab, except you don't have to make a separate M file. That's kind of nice. Find currents of V, R1, R2, R3, and these underscores don't matter for now. And %% means not the previous output, but the one before that. And so if I define a function like this, now I have in clear form, I have the 4 currents in terms of the V's and the R's and so on. And when I run that function, I don't have to do a linear solve each time. And so then if I call the function with some numeric arguments, it produces the same thing than if I had just plugged them in directly. So that's kind of nice. You can make a function for it. You can manually substitute in values for the variables themselves. And there's another thing to point out here, which is that these are exact. With Matlab, you're dealing always with double precision floating point numbers. But here, Mathematica has solved these exactly and plugged these exact precise numbers in. And so this rational number is the exact output, exact number that for that current. If you want something that looks more like a number like you would have in Matlab, like a machine precision number, n is the function that will just convert all these numbers to machine precision. OK, so just to sort of, where do we start, where do we end? We had a circuit. We had some equations that were given to us about the circuit. We wanted to find the currents given the voltage and the resistances. And we pretty much transformed that problem using coefficient arrays into a linear algebra problem and then solved the linear algebra problem. If you were in the real world and you had a circuit sitting before you on your desk and you could read the colors on the resistors and you knew what voltage you were pumping in and you wanted to know what currents you were going to be going through those resistors, you could, maybe if you were lucky, transform that problem into a linear algebra problem and solve it. But it would be more direct if you could just say, I have a set of equations due to Kirchhoff's law and so on, and I would like to solve those equations for these variables. If only there were a way to do that, there is a way to do that. So why not solve directly for the currents? I have these equations here. I want to solve these equations for these variables. Bam. What immediately comes out is the solution, just like when we were doing the example at the beginning with the quadratic equation. So here's the 4 variables. It's not just x now. The 4 variables that we're interested in. And these little rules, these little arrows, tell us what their corresponding solution is. Again, if I take that previous answer and I plug in R equals 5, V equals 5, and the resistors are all 100, I get these rules which point to specific exact number answers. And then I can do n of that, and I get something that I can compare against Matlab. So this is what I would do if I were in the real world and I had some equations and I wanted to solve them for some variables. I would not try to do anything fancy where I could possibly make some errors by transforming them into linear algebra. I would want to be able to check my answer as directly as possible with as few elaborate steps as possible. So I feel that a one-step solution is a pretty nice way to go about it. OK, so so that's one of our 2 examples. Dun-dun-dun. So in conclusion, we were able to express this. We were able to express our solution using nice formatting tools. We were able to paste in parts of the problem statement that let us sort of keep track of what we were trying to achieve. And we could use very direct functions in order to solve for what we wanted to. And it's nice to have the inputs and outputs adjacent because that helps us sort of keep track of what are we trying to do in this problem. It's not like there's a whole big pile of input code that you execute and then it spits out a whole bunch of stuff that you have to map back. So anyway, OK, so that's the first one. Let's talk about the second one. So this is you probably remember this from, I think this homework was due last week for you. This was an ODE problem. And it has to do with looking at kinetic and potential energy. OK, so you. Let's see. Yes, you. OK. So I guess I won't go into all the grisly detail, but I formatted some stuff, pasted in the problem statement, cleared out my old variables. And here we have, I'll just run this program just to make sure that it'll evaluate the whole notebook. Boop-de-boo. and done. OK, so same kind of thing. I've defined some variables. Here's some like the initial position and the initial velocity. I call dsolve like I did in the second slide with this ODE that the problem gave to us, and it spits out this big long thing. OK, so this looks horrible, but having the analytic solution to an ODE can give you a lot of insight into what's going on mathematically, more than if you just solved it in Matlab. So if you solved it in Matlab, if you remember, you would have to like make this like transform it into a vector of first order equations and then make an M file for that and call ODE 23 or whatever. But here, right out of the gate, you get this. So there's a cosine and a sine of something times t, so you know that the answer is going to be like oscillatory, and then it's being multiplied by e to the minus t. That goes down. So you would expect this solution to look like a decaying an oscillatory decaying exponential. And sure enough, if you plot it out, you get the decaying exponential. So let's see if we can do anything more with this. I'm going to use another manipulate command like I showed you at the beginning, and instead of it being a big plot, it's just going to be some graphics, some like graphic objects. It's going to be a point whose two-dimensional coordinates are x and 0. So it's just going to be on the x-axis, and this plot range is sort of showing how big of the plot we're going to show, and please make a small image, and run from t goes to 0 to 10. So if I run this, let me scroll it up a little bit so you can see a little better. Okay. Boop. The little point goes back and forth, sort of like you would. So this problem is originally there's a spring and a block is moving back and forth, and this is showing you exactly that. Here's the little block that's moving back and forth, and that's the position. So I just love it. You can see immediately whether or not your solution is even reasonable. Here's another example. I added in just like a line, and I made the point a little bit bigger. So now you can see sort of the spring. This line is supposed to be like the spring. And just in a little handful of code that once you kind of get the gist of it is not super, there's nothing really, there's some syntactic things that are unlike Matlab, which are a little bit weird. But other than that, you can sort of read this and say, yeah, I'm making a point and a line, and that's kind of the gist. That's all that's happening here. OK. So let's just stop this. OK, so what next? So the next part of the problem is to compute the kinetic and potential energies. And so because the Mathematica front end has some really nice typesetting abilities, this looks just like 1/2 mv squared. X prime is v. This looks just like 1/2 kx squared. You can write in ways that are very directly linked to the concepts that you have in your mind, the equations that you would write down on paper. And then without too much trouble, you can plot the kinetic energy, potential energy, and total energy from t equals 0 to 5. And it's really easy to add legends. It's just sort of that. OK, so that's kind of nice. But let's make it even cooler. Let's see if we can combine this plot and then the one before with a little line going back and forth. Without too much trouble, I just pretty much copied and pasted this code. So this is the line and the point going before. This is the plotting command with this little epilogue thing. This epilogue thing says, after you're done with the plot, I would like you to add a line that goes from t0 to t3. And I'll show you what that means in a second. It's easiest just to sort of play it and see what's happening. So this is the line that's in the epilogue that we're drawing again and again. So this is as time is going, as time is progressing, the ball is going back and forth. And this is really nice. This lets us, in a very intuitive way, look at certain points of interest. For instance, let's see. So the kinetic energy is blue. So here the kinetic energy is 0, and here the potential energy is sort of maximized. Well, look, that corresponds to when the spring is all the way stretched out and the ball is not moving. If we go to the next point, let's just drag this slider over, we can see that, whoa. We can see that when the potential energy is 0, that's when the ball is when the spring is pretty much not stretched at all, and the kinetic energy is maximized, meaning it's going as fast as it can. OK, so with just a handful of code, you can sort of build up your results so that you have this like pretty nice animation. I think in this problem, we give the students like our own M file that you can run, and it will do this for you. But look at, once you get the hang of it, without very much code at all, you can make your own animation. I think that's kind of neato. OK. And let's see how we're doing on time. Yeah, I'll sort of breeze through this real quick. In hindsight, I'm not going to breeze through this real quick. I think there's other cool stuff. Let me just show you this one last thing. So this is for the next part of the problem. There's a different ODE, and you can solve it. You can solve it, and it will do the numeric. It won't be able to solve it analytically, so it will do the numeric solution in a way that's a lot easier than doing it in Matlab. And you can get a situation where your three different initial conditions. One of them, it just wiggles back and forth a little bit. The second one, it starts out upright and then tips over. This guy. Whoa, tip over. OK. And in the third one, he starts down, but then he has this initial kick, this initial big velocity that causes him to fly around and do a whole circle. There it goes. Whoa, there he goes around. So without too much trouble, you can visualize all these solutions, whereas before you would just have to plot some graphs. Is this the right answer? Who knows? It's the same as my friend. Turn it in. Like that's what I did until I learned that I could get a little more insight with Mathematica. OK, so that's that. Let's go back to this thing. Yeah, I had this problem before. All right, Mathematica, you have betrayed me for the last time. Yeah, OK. Yeah, so we did that. This is just a reminder of what you have to do in Matlab if you want to simulate these things. So here's mx double dot plus bx plus kx equals 0. First you have to vectorize. So you have to pick a couple of intermediate variables. This is all, I'm sure you're acutely aware of this because you're currently in the class that's teaching you this. And you have to express the derivatives of these intermediate variables in terms of the ODE. This is so that you can turn a second order equation into a vector first order equation. And then you have to make a MATLAB, you have to make a MATLAB function that essentially encodes the right-hand side of this. So here's the x2, and here's the minus 1 over m times blah, 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 minus 1 over m times blah, blah, blah. So this is all in the name of making this into a function that MATLAB will recognize and be able to numerically integrate. And then you have to call ODE 45 with this function handle. OK, now the point, the point that I want to make is, ugh, this is a lot of work in order to translate what you want to do into a numeric answer. It's a lot of work to have to, it's not just this is a lot of work. You have to contort your thinking. You can no longer think, what is the solution of this ODE? You have to think, what are the sequences of steps that I have to do in order to make MATLAB solve this ODE? It would be so nice to use the right tool for the job and be able to just sort of say, solve this ODE, not have to contort your thinking. We all have to do it. We're all, like, everybody uses MATLAB, and we all have to know how to numerically integrate ODEs, so we all have to do it. But it would be nice if there were a more natural way. OK, so we talked about that already. Yes, it would be nice if you could more directly write code that would find an answer for you that could have some sort of intuitive interpretation. And it would be nice if you could visualize your solutions easily so that you could get a sense for what's actually going on in the problem. OK, so the second part is done. By the way, we're going to finish early enough that if anybody has a 1 o'clock class, you can all easily make it. So there's 10 minutes left in this. OK, so I think I really like Mathematica because when I would do my homework in it, it's much easier to go back and see what the heck was I thinking. I can use functions more directly in order to check my answers or so on, and I don't have to worry about losing myself in intermediate steps. And it ultimately gives me sort of a deeper understanding of the problem. OK, so let's talk about power. Mathematica, so Matlab was designed to be, initially, Matlab started out like in the 80s as a nice wrapper around a Fortran library that did linear algebra. So it was born knowing that we want to do matrix calculations. MATLAB stands for Matrix Laboratory, as you probably know. Mathematica, in contrast, Stephen Wolfram is kind of this crazy genius who made Mathematica, and he wanted this computer system that could do any computation that he could think of. He wanted general computation to be able to be done in this program. And so that's sort of the philosophy behind it. And as you can see, there are just so this obviously this is a Mathematica page. They're going to talk about how awesome it is, right? Okay, but here's a page where they talk about all the different other programs, so these are all like different domains. So there's like, audio synthesis and, math education and doing statistics and stuff. And there are specialized software packages that you get if you want to work in that specialized domain. So down here, for instance, under numerical matrix systems is Matlab if you want to work with numerical matrix systems. But the point is there are a lot of domains, and in each one there are specialized tools, but Mathematica also has some tools that can help you. Okay. There are over 100,000 examples in Mathematica. When you buy Mathematica, there's like something like 5,000 built-in functions. You don't have to know all of them, but among those 5,000, there are like 100,000 examples of how to use those functions in the forms of guides and tutorials and so on. And so, for instance, here's the documentation for plot label. So plot label is just an option. It's not its own function. It's just an option that you can pass to the plot command. And you can give it whatever string you want, and it will put it in the plot. You can edit. This is not the default value for this documentation, but the documentation, if you can tell from these little cells here, the documentation of Mathematica is written in Mathematica. And so you can go in and edit it, and it won't save those changes unless you really want to. You can go in and edit it and add your own strings, try out the function, tweak it in accordance with the examples, and then copy it and paste it back into your own code. So this makes it super easy to say, oh yeah, how do you use this thing? Okay, great, copy, paste, now it works in my program. What else? Okay, kind of fun. There's a couple of things they've done in the last few years that I think make it really cool. So if you say Wikipedia data of UCSB, Matlab will go out and retrieve the text of the Wikipedia page for the University of California at Santa Barbara. So it's this big long article, and it gets the text. Okay. If you pass that text through the function called delete stop words, so it deletes the very common words like a, and, the, of, but, and so on, and then you pass that to the word cloud function, it will draw you a nice word cloud of this Wikipedia page. Okay, so that's nice. And sort of the bigger words mean they occur more frequently. The word UCSB appears frequently, university, campus, Santa Barbara, and so on. Okay, and there are all sorts of options. You can change the shape. It doesn't have to be a circle. You could do all sorts of crazy stuff. Okay, so suppose that I thought this was really cool and I wanted to share this with my family, but they don't go to UCSB. They don't think UCSB is as great as I do. They want to be able to put in their own things. I would like to be able to make like a web app for them where they can put in their own string. It'll search Wikipedia data for it, and it'll make their own little word cloud. Here's how to do that. You pretty much take this Wikipedia data, pass it to delete stop words, and run it through the word cloud, and you wrap all that in this thing called a form function, which you then cloud deploy. So obviously don't memorize this. I'm just trying to show you that it's not too long of code to do. You pretty much do this thing called cloud deploy of this function. And what comes back is this cloud object thing, which is essentially a URL. And if you point your web browser to this URL, you will be faced with a form. That's where the form in the form function comes from. You will be faced with a web form, and if you type in UCSB to it, it will return this picture, the same picture that you had before. The thing to note here is that you do not need, anybody with a web browser can do this. So my aunt comes here, she writes in petunia, okay? And next thing you know, she's looking at a word cloud for petunias or whatever. So she does not need Mathematica. She does not need to know anything about programming. All I need to do is email her this URL, and she can use it. This code has been deployed to Wolfram servers, and it is running on their servers. Your code has been running on their servers with this cloud deploy function. Okay, and please come talk to me if you want to know a little bit more about how to set that up. Okay, I think that's very cool. I have two more examples, and we're well under time, so don't panic. My success as a grad student is I can attribute Mathematica for. For my research, I do some information theory-based stuff, and I needed to prove that this equality happens. So this is some function of like gamma, and it's parameterized by n, and if you crank up n, I wanted to show that this function approaches this function of gamma. Okay, so obviously we're not going to talk about all the details, but it was real easy to throw this over the fence to Mathematica, use their nice sort of built-in type setting, so you could sort of tell that I wasn't, so this is nice to be able to type it in a nice way. And then here's this function that's parameterized by n, and I want to show that as you crank up n, this thing approaches the orange thing. Okay, and so as you crank up n, it looks like it does it. The mathematical proof of this, so we got a couple of papers out of this, and it was more that, but that was a critical technical element in our papers. And this is what we made with Mathematica, and this is all the math that was required in order to show that very natural thing of this thing goes to that thing. In Mathematica, it was so easy to just see that that happened, and then later, once you see that, my advisor sees this, he says, "Great, we'll prove it later. Keep going. Figure out what other research you're gonna what can you do with this now that you found it. We'll figure out how to prove it later." If I had to prove all of this stuff before I could make any more progress, I never would have written those papers. But being able to sort of see that it pretty much works, by dragging the slider was a great stepping stone. Last thing. This is, I was going to go see Book of Mormon with my girlfriend. And the tickets were expensive. And I was using StubHub. So on StubHub, you can post, vendors can post different amounts of tickets and stuff, and different prices, and different places in the orchestra, in the room. And I wanted to get a good deal. So I downloaded the ticket data from StubHub, and I wrote a Mathematica program that, here's just a zoom in of it, where very easily I could just check how many do I want, what price do I want, where do I want them to be in the section, what row do I want. StubHub will let you search for some of these things, but for instance, I don't think they'll let you search for the row. So if you say, I want to sit in the center orchestra, you could be all the way back. Too bad. I would like to be able to say, I would like to be specifically in these seats here. And the result of all this, so here's essentially the heavy lifting code. If you want exact seats and you have the exact quantity, if the price is less than some threshold and you're in the section that you want and the row is less than, not too far back, then select the tickets based on that criterion. And what this does is it presents it to you as a nice bunch of tabs here. So you can say, oh, $275, that's the cheapest that I can get these tickets for. So this is kind of a minor thing. It was really fun to write, and I felt pretty good. I felt like I got it was a great musical, but it's really expensive. But anyway, I felt vindicated that I could use Mathematica for that. Okay, so in conclusion, well under time, it's free to try in a number of forms. It lets you express your ideas clearly and cleanly. Clearly because you can format things nicely, sort of the way that you would have them in normal math, and cleanly because there's a ton of built-in functions that you can use at your disposal so that you don't have to contort your ideas into something unrecognizable in order to solve your problem. It's powerful and useful. They've been trying to find all sorts of cool ways, things that you can do with it, deploying web apps and making sort of manipulatable GUIs and stuff really easily. And there's even more that I would love to talk to you about. So I found great success with it at UCSB and beyond. And so good luck on your successive endeavors. And please fill out the poll. I would love to know how I did, if you want more of these kind of things, what you would like to talk about, and you can keep the pens.
Justin, can I ask you a question?
Yes.
So we all see that it's very friendly. I mean, once you have nice code running, all this graphic stuff and notebook, it's always very nice for us to look at the Mathematica. But what do you think about when you have something wrong? I mean, most of the cases we're struggling with commas, brackets, missing syntax in the function. So how friendly is Matlab in this part? Sorry, Mathematica in this kind of situation?
Mathematica is famously hard to debug. There are some things that you can do that one thing that you can do to debug it is there is a function called trace, which will print out it takes your initial expression that you're trying to evaluate and shows you everything that goes on under the hood as it's trying to execute, as it's trying to evaluate that. And that's sort of the best thing that it has. Allegedly, there are some things like the Mathematica debugger where you can apparently set breakpoints and stuff, but that's hard enough. It's hard to learn. It's certainly not as easy as in Matlab just being able to set a breakpoint or something, and that has to do with how Mathematica evaluates expressions under the hood. I will say, just as a follow-up, just so it's not totally perilous, that there is if you don't want to use the Mathematica front end, there are other ways of running Mathematica, and one of them is to use a product called the Wolfram Workbench, which is essentially an Eclipse IDE plugin. You're probably familiar. I know you're familiar with Eclipse, and in there you won't have access to the nice integral signs and stuff, but you will be able to use the Eclipse debugger. Yeah. We have, if people want, I left a spot where you can leave me your email address if you want to stay up to date on these things. We also have like a Facebook group that, let's see. I'll see if you can find it because the event that, this event was put on by the UCSB Mathematica page. So if you'd like to know more, you can go there and like that page and whatever. David. Yeah.
When I finally graduate from UCSB and I no longer have a free license to Mathematica, and I want to open up all of those .md files that I made while I was here, will I need to buy a license with Mathematica, or is there some pure text editor that can open it and it's in a repo?
Notebook files are represented under the hood in a plain text format, so it's not like opening a .doc in a text editor where it's totally indecipherable, but it's not the friendliest format to open it in. There are formats, like you can export to PDF really easily, and you can export to a thing called CDF, computable document format, which will retain all of the interaction. So if in CDF, if you have a CDF viewer, which they make free, you can still use all the manipulates and stuff. Yeah. Cool. And it's 12:45, so you'll have plenty of time to get to any classes that you have at 1 p.m. Please feel free to talk to me, and thanks again for coming. Yeah. All right, thanks. Yeah, just leave all the flyers there. I'll come pick them up. I got to clean all this stuff up anyway.